Okay, YouTube, in this video we're going to be looking at what we call recursion formulas, or for something to recur. I want to start with this, like if you look up this term on the internet, I probably should have looked this up before I opened my big mouth, but to recur means like happen again. So we say like happen again and again or something like that. But like a recurrence or something like that. It's for something to happen again. Basically, what we're looking at are terms of a sequence that are defined by terms that occurred before it. So when we looked in our first video at the Fibonacci sequence, we were looking at this sequence that looked like this here, 1, 1, 2, 3, 5, and 8 here. I can't remember how far we got, but basically this sequence here is defined by saying to get the next term, what you got to do is take the two terms before and add them together. So you can see 1 plus 1 is 2, and 1 plus 2 is 3, and so on and so forth. So like naturally, 5 plus 8 would be 13. That would be our next term. 8 plus 13 would be 21. You could see how this sequence would carry out infinitely many times just by using the terms prior to the term that you're going to get next. So that being said, when we say things are recursive, we're saying that they are defined by using terms that occur before it. So recursion formulas are what we're going to look at in this example video, and we're going to kind of compare and contrast it with what we call it the explicit form of a formula. So we say the formula is used for the nth term of a sequence, expressed the term as a function of n, the number of the term. So we'd say sequences can also be defined using recursion formulas. Now recursion formulas, they define the nth term of a sequence as the function of the previous term. So again, I would say that I can tell you what this term is right here, an plus 1, say. And I would say that an plus 1 is just one term beyond the nth term. So again, like with a sequence here, let's write it this way. We'd say that the terms of our sequence are thus. We would say a1, a2, a3 is the third term, and so on and so forth. I would say then let's do this, n minus 1. The next term would be the next term after the n minus 1th term, which would be the nth term. The next term after that would be the n plus 1th term, da 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 da. So what you can see is that when we represent this formula here, what we're going to say is to get the n plus 1th term, we're going to have to do something with the nth term, and maybe even the n minus 1th term, as in the case of the Fibonacci sequence, we used the previous two terms. So this example here, we're going to illustrate that if the first term of a sequence is known, then the recursion formula can be used to determine the remaining terms. So looking at this here, what you're going to see is this. It says find the first four terms of the sequence in which a1, oh, so cool, we have our first term right here. We should label this. This is our first term, where a1 is defined as having a value of 3. We better write this down, 3. We want the other 3 terms out of the 4. But we know the first term is 3, and this is true. Now notice it says this, an is equal to 2 times an minus 1 plus 5. So what I'm going to do is I'm going to write a translation for you here for the very first time you're seeing this. What we're going to say is this. We're going to say the next term up, which is our nth term, or let's do this. Let's put it this way. Any given term, we say the nth term, is equal to 2 times the term that's going to be long, term before the nth term, plus 5. I'll put that in here, plus 5. So basically, what this is saying is you got to read it critically here. We're saying to get the next term, what we're going to do is take the term before it, double it, add 5 to it, then you get the next term. And it says this is true for all n values greater than or equal to 2. So without getting into the technical detail here, what we're going to do is we're going to say this. If I want the next term here, this term right here, what we're going to do is we're going to take the third, or the first term here, 3, we're going to take it times 2. We're going to say 2 times 3. We're going to add 5 to this. And so 2 times 3 plus 5, we're going to get 6 plus 5, we would get 11. And I'm going to put my 11 here, 11. So now what we're going to do is we're going to take that 11, we're going to say, take it times 2 and add 5 to it. Because what we're going to do is always take the term value before it, double it, and add 5 to it. So we would say, if we put this 11 in here, you can see how this is happening again now, recur. We'd say 22 plus 5. We would get this, 27. That would be the third term in our sequence. And then what we do is just the same thing again, 2 times our input plus 5, and we would say that right here, 27. We would really get this, 2 times 27 is 54, plus a 5 is 59. So this would be our first four terms of this sequence here where it's defined recursively. So what we're going to do is write a really quick set of notes here for recursive sequences. Recursive sequences. One thing has to be true. Must already know the first term value. Must already know the value of A1. Okay? And then we must, try that again, must define the nth term in terms of previous terms. Okay, and that's an interesting thing to do, but that's how we refer to recursive things. So just be prepared to see some things that are defined recursively as we move forward with our formulas. Cheers.